So thank you for attending this presentation. I hope you can hear me well. Okay, my name is Joy Ndiwa. I'm a PhD fellow at Center for Epidemiological Modeling and Analysis, University of Nairobi, under the African Modeling for Analytics Women project. I'll be taking you through our work as a group of 5, me being the leader. So today we are going to be discussing on modeling the impact of routine treatment on schistosomiasis elimination in Kenya, which is my disease of interest for my PhD. So, sorry, took time for the slides. So, schistosomiasis is a parasitic disease, which is caused by a macroparasite of the genus Schistostoma. In Kenya, we have 2 primary species, which is the Schistostoma mansoni and Schistostoma hematobium, that is responsible for urogenital and intestinal schistosomiasis, respectively. According to the prevalence in Kenya, approximately over 6 million people are at risk of the disease, and at least approximately of 2.5 million are already infected, with a population of approximately 50 million. So as from the far end of the map, we see that the prevalence of schistosomiasis in Kenya significantly varies according to the regions, and the map is up to the granular level of the sub-county level, which is the sub-county level, which is the implementation unit for schistosomiasis. So we have areas that have low prevalence, moderate prevalence, and high prevalence, and we also have sections where the different levels of prevalence are also in the same area. Like we look at the Lake region, we have areas with low prevalence, at the same time areas with moderate prevalence. So that disaggregation of the prevalence prompted us to not just use a simple mathematical model like a compartmental model, but to move into an agent-based model. So currently in Kenya and even globally, the disease is targeted for elimination, and globally, according to the WHO guidelines, it's targeted for elimination as a public health problem. And in Kenya, it's targeted for elimination by reducing the prevalence to be below 2%. So to achieve this, we have guidelines according to WHO. So for WHO, for preventive chemotherapy, since we have different ways of the interventions, specifically, we are interested in looking at the preventive chemotherapy. And for this, we conduct mass drug administration. According to the guidelines for WHO, we are supposed to do for different areas, depending on the prevalence level, either once in a year or twice in a year. And in Kenya specifically, we do annual mass drug administration, and we target individuals above 2 years. But what is happening in Kenya, we only target 5 to 14 years. So for this specific project, we are addressing the challenge of maintaining the therapeutic coverage, which is, according to WHO, supposed to be 75%. And this is contributed by 2 individuals, where one individual, will call them never treated individuals. These are individuals after the multiple, let's say we do mass drug administration this year, next year, like in the 5 years, we'll have individuals who remain not treated due to different issues. And then we'll have another individual called not treated because maybe they're not within the bracket of the 5 to 14 years. So they remain not treated during the mass drug administration. So these 2 individuals are going to be contributing to the eroding of the therapeutic coverage attained during the mass drug administration campaign. So to address this challenge, in our group, we propose to have a routine house-to-house treatment after the mass drug administration. And the intention is to reduce the risk for the disease and also accelerate the time to elimination of the disease. This prompted us to the question of how we are going to we're asking ourselves how the implementation of this routine house-to-house treatment can help accelerate the time to elimination. So we have the 2 objectives that we are intending to achieve with the ABM model, which is first to model the transmission dynamics, and then now we can do the house-to-house treatment at the mass drug administration. So on to the model structure. Since the disease is a macroparasitic disease, so since a macroparasitic disease, then we cannot ignore the interactions between the different hosts, because here we have the human host and we have the snail host. And now, since the parasite also lives outside the 2 hosts, then we have to tackle the environment. So for the model, we'll we consider the human host, the snail host, and also the environment. The human host is an agent, the snail host is an agent, and also we have the households where these individuals are living in also as an agent. And plus, we're also considering a multi-level agent-based model. So we have a child living in a household, and that household within a community, and then that community within different communities within the same area. So for the routine treatment where the intervention is done between, just from the model, to reduce the number of eggs that are going to be produced. So for the routine treatment, we're going to use the model on the far right, where, just to give an example, we have the community health promoter. They first check the master organization eligibility, so they'll conduct the MDA. So during the conducting, they'll first look at the eligibility, whether eligible or not. So looking at the not eligible, if you're not eligible, they check the age. If you are going to be below 5 years, they check if you're going to be turning this year for the master administration. If yes, then they do the routine treatment. If not, they will going to update the model as not treated. Then on the other end, the same. So we add assumptions. If we could have used the STARSIM model the way it is, the first is the homogeneous mixing and the different assumptions. But then we noticed that this disease cannot be able to be modeled using the STARSIM model the way it is because of the first challenge of homogeneous mixing. So we decided that our next steps will be first to come up with the transmission model to really capture the heterogeneity of the disease. Then we'll do the scenario modeling, and then we'll be able to present the results. Thank you.